Great. Thank you very much for inviting me. It's a great pleasure to come and to talk to you today. I'm going to talk about what causation is and how we can identify it. I'm going to focus more on the identification, but I'll hopefully talk a little bit on what causation is. So first of all, I'm going to talk about the link between causation and correlation. We all know that causation isn't correlation, but we don't all know quite what the relationship is between the two. And it helps when we want to understand how to identify causation to be clear about the link between cause and correlation. Then I'll talk about how we identify causation and methods, a variety of methods for identifying causation, and I'll talk in most detail about one approach, the EBM plus approach to identifying causation. Okay, so we all know that causation is not correlation. The question is, what makes a correlation causal? That's a fundamental question if we're going to be able to infer causal relationships from evidence. So you might have an observed correlation between two variables. There are, in fact, a large number of possible explanations for that correlation. One is causation, so A is a cause of B. Another is backwards causation. Another is confounding. We heard quite a lot about this morning. So there's some variable that hasn't been controlled for in the study. Then there are other sorts of bias. There are actually quite a lot of sources of bias that you might consider. I've listed a couple here. There's performance bias and detection bias. Most statistical methods kind of only work asymptotically. So whenever you have a finite sample, there's always going to be a chance that associations are entirely spurious. And obviously you can control by taking large enough samples to reduce the probability of that chance, but there's always one possible explanation is just sheer coincidence. Fishing, this happens quite a lot. So you measure so many outcomes that there's likely to be a correlation between your variable of interest A and some outcome that you're measuring. Temporal trends, so the variables might both increase over time for independent reasons, and the correlation between the two may be attributable to that independent increase over time rather than any causal connection between the two. And then you have a variety of non-causal connections between variables that can give rise to associations. One of these is semantic relationships, so variables with overlapping meaning are going to be associated normally. Constitutive relationships, if one variable constitutes a part of another, that is going to give rise to correlations. Then you have correlations due to logical complexity. Even physical laws and mathematical relationships can give rise to correlations. So the important thing to emphasize is there really is a large number of possible explanations of any particular correlation. And the task of causal inference is to rule in the top explanation as being the most likely explanation, the best explanation of the correlation, and rule out all the others as being the least likely or the least plausible explanations of the correlation. Now there's one thing that's distinctive about that topmost explanation of a correlation, the causal explanation. If it's genuinely the case that A is a cause of B, then there's going to be some combination of mechanisms that explains instances of B by invoking instances of A. So there's going to be some mechanism linking A to B that is used to explain B in virtue of A, and that can account for the magnitude of the observed correlation. So this is the real distinctive thing about the causal explanation of a correlation in comparison to these other explanations of a correlation. So we can say that if you want to infer causation, so you want to go beyond correlation, what is it that you need to do to go beyond correlation in order to infer causation? Well, somehow or other, you need to infer the existence of an underlying mechanism of action, because that's what's distinctive about causal connections. So in order to establish causation, you need to establish two things. One is that the variables you're interested in are correlated, and the second is that there's some mechanism linking the two variables, that you can explain the effect in terms of the cause. The important thing to note here is you only need to establish the existence of a correlation and the existence of a mechanism. You don't necessarily need to work out the magnitude of the correlation in order to establish causation, nor all the details of the mechanism. What you're trying to do is establish that there are both of these things. So this kind of account of causation brings mechanisms to the fore. Mechanisms are an area that philosophers of science have studied in some detail in the last 20 or so years. And they can be categorized as follows. So one class of mechanism is what's sometimes called a complex systems mechanism. These are entities and activities organized in such a way that they're responsible for some phenomenon to be explained. For example, the heart can be thought of as a complex systems mechanism. It consists of entities and activities structurally organized in order to pump blood. So it's a complex of interacting parts. Another kind of mechanism is a spatiotemporal process along which you can propagate signals. So here you can think of a mechanism linking an artificial pacemaker, the process that links the pacemaker to the heart. You have a cable basically, and that propagates a signal from the pacemaker to the heart. And that can be thought of as a mechanistic process. And then you might have a combination of the two sorts of mechanisms. So you have a complex systems mechanism by which the individual's pacemaker produces the signal, then that propagates down the cable to the heart along a mechanistic process, and then you have a complex systems mechanism of the heart. And the interaction between these three mechanisms gives rise to the heart pumping blood in the correct way. So this is the way that philosophers of science have been understanding mechanisms. And when you bring mechanisms to the fore in causal inference, the question is how you establish the existence of these sorts of things. So how do we establish the existence of mechanisms as well as correlations? Well, there's two approaches. They're both in practice, they're both used. One is more systematically entrenched than the other. I'm calling the two approaches a monist approach, which is the kind of standard approach, which is very well entrenched, and a dualist approach, which is non-standard, but I think the right approach. So here's the monist view. The way to establish existence of correlation and existence of a mechanism is by careful use of clinical or epidemiological studies that measure these variables together, A and B together with potential confounders. And the way you infer causation is you disconfirm other possible explanations of the correlation. So you establish that there is a correlation, and then indirectly you establish that there's a mechanism linking A to B by ruling out in turn all these other potential explanations of the correlation that I showed you earlier. I think this monist view is quite well entrenched in evidence-based medicine and in statistical approaches to causal inference. So it seems to be the kind of the view that the mainstream are trying to push in a large way. That really, in order to establish causation, you need to just consider clinical and epidemiological studies. I want to contrast this with the dualist view. And here you have clinical and epidemiological studies, and these play a very important role in establishing causation, but they're just part of the picture. You also have mechanistic studies, and these confirm or disconfirm specific mechanism hypotheses. So these are mechanisms of action that have been proposed in the literature to account for correlation. Normally, when someone puts forward an association that they think is causal, they will try and hypothesize one or more mechanisms of action. And these can then be tested according to how well they fit with the actual mechanistic evidence that's available. And mechanistic studies can be relevant to whether these proposed mechanism hypotheses are correct or not. This is the way we used to establish causation when we used Hill's methods, Hill's criteria more systematically. So Austin Bradford Hill, he was one of the pioneers of the randomized controlled trial, and he put forward his list of criteria for establishing causality. Many of these criteria deal with the way in which clinical or epidemiological studies support correlation and mechanism. But some of the criteria, he's got three criteria called plausibility, coherence, analogy. These deal, you can conceptualize these as handling confirmation from evidence arising along these pathways, the M pathways that I've labeled in this picture here. So these are about fit of the causal connection to biological evidence, evidence of the underlying mechanisms. This kind of dualist view is also explicitly used by some organizations in their evaluations of causality. For example, the International Agency for Research on Cancer explicitly has a stream for analyzing mechanistic studies and evaluating these studies and integrating evidence of mechanisms alongside clinical and epidemiological studies in order to establish a causal claim. And they've got quite a well-developed procedure for deciding, on the basis of a range of mechanistic studies and epidemiological studies, whether you can conclude there is a mechanism of action in humans of carcinogenicity of the substance they're evaluating, and then they can use that to infer causality. So the way I see it is kind of Bradford Hill in the 40s and 50s was working on these problems and adopted a kind of a very broad view of the nature of evidence to include mechanistic studies as well as clinical and epidemiological studies. And then somehow the focus has shifted much more strongly towards these large statistical studies and away from the evaluation of mechanistic studies in subsequent years. And this is largely attributable to the evidence-based medicine movement, which really pushed evaluation of randomized and observational studies to the exclusion of other forms of evidence. But nevertheless, organizations who have to do this in practice often recognize the importance of properly evaluating the mechanistic evidence as in addition to the clinical and epidemiological studies. So this brings me on to the EBM plus approach. The core idea behind EBM, so EBM plus is intended to be a development of the evidence-based medicine approach. The core idea behind EBM is to make your evidence and the methods of evaluation explicit. So instead of just having these committees where people sit around tables giving their opinions on whether A causes B. You really try and articulate what the evidence is and also the methods for evaluating that evidence. And arguably this has led to much better scrutiny of evidence and great improvements in healthcare. It's also led to improved understanding of what I call C-channel confirmation. So along the left-hand side here. However, EBM, as is quite widely recognized, is a pretty dogmatic and dogmatically adheres to the kind of monistic view of establishing causal claims, which is this view, because it prioritizes clinical studies over any other kind of evidence. I'll just give an example. So this is what's known as an evidence hierarchy used to train students in medicine on evidence-based medicine. So you have your systematic reviews and meta-analyses at the top of the hierarchy. These review clinical studies and come up with an overall opinion. Randomized studies, observational studies. Then worse than any of these studies are ideas, editorials and opinions. And then your kind of bench research, your mechanistic studies are even lower than opinions in the view of kind of mainstream EBM and sit right at the bottom of the hierarchy. And this isn't just one, it tends to be the case that any hierarchies that do mention mechanisms puts mechanisms at the bottom of the hierarchy. So the EBM movement has really pushed for this exclusive focus on clinical and epidemiological studies, and in a way the kind of the professionalization of the statistical approach to causal inference has kind of gone in the same way, because it's really focused on statistical techniques for evaluating large studies to the exclusion of other forms of evidence that might be relevant to the problem at hand. So the EBM program, which is a kind of network of researchers interested in this, is trying to understand the M-channel, what I call the M-channel conformation, which was the right-hand side of this picture along here, in a bit more detail. So try and make that more explicit, which is, after all, the aim of EBM, is to make the evidence more explicit and also the methods for evaluating the evidence more explicit. And we've also been trying to come up with general methods for evaluating evidence of mechanisms. So coming up with some heuristics that help to evaluate mechanistic studies, help to decide when specific mechanism hypotheses have been established or not by the evidence, and help to assess how the establishing of specific mechanism hypotheses feeds in to help support a causal claim. So developing methods for integrating evidence of mechanisms with evidence of correlation. And one thing that we produced in our project is a handbook on considering evidence of mechanisms in the health sciences. And this will be available freely online in about a month or so, so you'll be able to access this then. In our handbook, we split the book into 4 parts. There's an introductory part on what mechanisms are and why it's important to consider evidence of mechanisms when you're evaluating claims in the health sciences. Then we put forward tools for working with mechanisms. Different organizations, different groups of people use different tools systematically for reviewing evidence. So for example, we worked with the National Institute for Clinical Excellence in the UK, NICE. They tend to use grade tables for analysing their evidence. And so we come up with a modified grade table that can help you analyse mechanistic evidence as well as the clinical studies. And then in the third part of the book, we developed some core principles for evaluating evidence mechanisms. So this is the kind of theoretical part, how to systematically gather evidence of mechanisms. This is quite hard because clinical studies tend to be quite well systematized in the sense that you've got databases that you can easily search through in order to find clinical studies relevant to an outcome. It can be harder to find mechanistic studies that are relevant to a particular mechanism of action that you might be interested in. Then how you evaluate those studies and how you evaluate the mechanism of action. And finally, how you use that evaluation to help inform your causal judgment. And then in the last part of the book, we talk about particular applications where this is especially important. So these are going to be areas where you don't necessarily have lots of high quality randomized studies. I mean, actually, the people we talk to on the drug approval panels and so on, they say they never have lots of high quality randomized studies. All the randomized studies are flawed in some way. But it's true that if you're assessing exposures, for example, assessing carcinogenicity like IARC is, then you're going to be dealing predominantly with observational data. In public health, it's very important to consider social mechanisms as well as biological mechanisms. So how will the population respond to advice? How will it respond to particular interventions and so on? And then treatment of particular patients is also an interesting special case. So as I say, this will be ready, this will be available in about a month's time if you're interested in this line of work. Here's I don't know how well you can see that, but this is a flowchart which gives our approach to what we advise in the book. So here you have a causal claim whose efficacy you want to evaluate. You've got clinical studies and their evaluation. If the clinical studies suffice on their own to establish or rule out efficacy, there's no need to consider mechanistic studies in addition. You can conclude that efficacy is decided one way or the other. However, in many practical cases, clinical studies and observational studies are far from conclusive. In which case, the kind of methods of the book come in, and it makes sense to formulate specific mechanism hypotheses and collect evidence in favor or against those specific mechanism hypotheses. Determine the status of the claim that there is a mechanism of action, and use that in conjunction with the clinical studies to help determine the status of the causal claim at the end of the process. So you're trying to work out, is your causal claim established? Is it maybe provisionally established? Is it arguable, or is it just speculative? Or have you even ruled it out? And the book provides some heuristics for doing that. Another question we address in the book is the question of external validity. This is another area in which it's crucial to use evidence of mechanisms. So with external validity, we're interested in the problem of, say, extrapolating from an animal population to humans, or one human population to another human population. We've established the causal claim in the source population. We want to know whether we can extrapolate that safely to a target population. There's a lot of skepticism currently about the validity of extrapolation. Can you really extrapolate causal claims from animals to humans in a safe way? But also there's quite a lot of work recently in philosophy about how you do support extrapolation inferences using mechanism-based reasoning. And so this is one question that we try and address in our book. So here you've got the causal claim that you're interested in the target population. You've got some different study population, and you've evaluated the clinical and epidemiological studies in that study population. You're trying to integrate the study population with further evidence on the target population. This tends to be relatively low quality evidence, you've got good evidence enough to establish causation on the study population, but your evidence directly on the target population isn't enough on its own. So you need to extrapolate from the study population to the target population. And then you can ask the question, do the studies on the study population establish or rule out the causal claim there? If they're decisive on the study population, then they can feed into your evaluation of external validity. So here you're looking for evidence that the mechanisms of action in the target population are similar to those in the study population. So this is called mechanism-based extrapolation in the philosophical literature. The way to safely extrapolate is to show that your mechanisms of action in the target population are similar enough to those in the study population. And then you need to somehow evaluate the status of this mechanistic claim and then determine the status of the causal claim from the status of the mechanism and correlation claims. So if you like, what we've been trying to do in the handbook is systematize and provide a few heuristics for approaches that have been developed over the last few years in philosophy of science for mechanism-based extrapolation. Okay, I'll just finish off by giving some examples as to why a dualist account to causal inference is preferable over a monistic account. So I'll start off with this tongue-in-cheek study. This says, you probably can't read the writing, but it says, parachutes reduce the risk of injury after gravitational challenge, but their effectiveness has not been proved with randomized controlled trials. This is a worry if you believe that randomized controlled trials are required to establish a causal claim. Of course, this shows they're not required to establish a causal claim. Why not? In this case, it's because you know the mechanism of action. The mechanism of action is very well understood. That helps support the observational evidence that you've got of successful parachute jumps. And by integrating the evidence of mechanisms with the observational evidence, that's enough to establish causality. You don't need a randomized study of parachutes in order to establish causality there. That's a kind of silly example which expresses why the dualist account is useful, but here's a slightly more serious example. So sometimes premature babies, their lungs aren't mature enough to be able to oxygenate the blood themselves. And this treatment was proposed called ECMO, or extracorporeal membranous oxygenation. And this involves taking the blood from the babies, oxygenating it artificially outside the body, and then pumping it back in. In initial observational studies, these suggested an increase in the survival rate of the babies that underwent this treatment from 20% to 80%. So a really marked apparent effect size. However, because the monistic view was mainstream and it was felt that you really do need randomized trials in order to establish causal claims in medicine, it was felt necessary to conduct randomized studies here. And in fact, 6 or 7 of these randomized studies have been conducted, and these have led to significant loss of life in the control arms, just to support the causal claim here. But it's been argued in the philosophical literature that this was completely unnecessary. And our way of seeing why it was unnecessary is that it's a bit like the parachute example here. You've not only got observational studies that demonstrate quite a substantial effect size, the mechanism is pretty blindingly obvious here as well. So this combination of having a well understood mechanism and observational studies that wouldn't be conclusive on their own, these mutually support each other, and are enough to establish causation. So I'd say the kind of form of inference that you're appealing to is this. You've got established mechanisms. Observational studies suggest a sufficiently large effect size, and sufficiently many studies point in the same direction. The mechanisms can clearly account for the effect size, and you can rule out some of the other explanations of a correlation, such as fishing, temporal trends, and some of the non-causal relationships I've mentioned. And there's no evidence to suggest a lack of a correlation in these cases, parachutes and ECMO. So you conclude there is a genuine correlation and a mechanism, and that allows you to establish causation. The observational studies don't even have to be very systematic, for example, the parachutes case, but also in the case of adverse drug reactions. Often observation there is entirely unsystematic, but in certain cases where you've got very good evidence of mechanisms, this can be enough to establish an adverse drug reaction and withdraw a drug from market, for example. Okay, and so this is the picture there. You've got observations, you've got other evidence of mechanisms. They're supporting both correlation and mechanism, and therefore they're coming together to support a causal claim. Hardline EBMers, sometimes called the EBM Taliban, they deny that you can ever establish causation without randomization. And they would just deny that causation has been established in these cases. But I think it's pretty intuitively obvious that these are cases where it's unnecessary to do randomized studies. Cochrane reviews are less hardline than the EBM Taliban. These are systematic reviews for evaluating evidence in medicine. They say we like to evaluate all the evidence, not just the randomized studies. However, in practice, they typically just evaluate the randomized studies. And if you look at the Cochrane review of ECMO, for example, it said, we exclude any study that's not randomized from this review. And this puts pressure on researchers then to randomize, even in unethical cases, such as arguably the ECMO case was an unethical case for randomization, because evidence reviewers will only consider randomized studies. And then there are others who admit that you do have causation established in these cases, but they can't offer explanations from within the EBM paradigm. So they tend to appeal to the Bradford-Hill criteria, for example, and so go out of the EBM paradigm in order to justify how you establish causation in these cases. But Bradford-Hill is a kind of dualistic approach. It's not in the mainstream monistic approach to causal discovery. Okay, I think I'll finish there and just conclude that so the monistic approach to causal inference is pretty widely entrenched these days, but it's not universally entrenched. I mean, even in drug approval meetings, the chair of the meeting will say, we only consider randomized studies, clinical studies, in deciding whether we approve a drug or not. And they bring these clinical studies to the table, and then they have a long discussion around the table, and about 2/3 of the discussion is about mechanisms of action and mechanisms underlying side effects and so on. So even in the drug approval case, mechanistic reasoning is playing a crucial role. It's one that hasn't been explicitly recognized and isn't being explicitly scrutinized, so that some of the mechanistic evidence isn't being properly challenged. So I think a dualistic view is a way forward, or maybe a way backwards, considering that Bradford-Hill originally put forward a dualistic approach. One worry is that you might not be able to review mechanistic evidence in a systematic way. I don't think that's a genuine worry. I think that you can say sensible things about how to review evidence of mechanisms, and you can integrate those reviews with your statistical analyses in order to come up with judgments of whether a causal claim is established or not. We're not going to do everything quantitatively, but we can still make judgments in the same sort of way as we do qualitatively at drug approval meetings and these kinds of conferences. Okay, so that's all I've got to say, and to put forward the dualistic view. Thank you.